All right, guys. Thanks for bearing with me. I hope to be back tomorrow. We'll see. So I wanted to go over on the notes today, um, how to do what we call ice problems. Ice problems are a big deal. This idea of ice, you'll see what it stands for. We use as a way to solve problems that deal with species and systems at equilibrium. So we're going to just cover how to solve them, how to set them up, how to solve them, and then some applications of them. And then I have the some from the practice today. Then after that, there's some practice questions that you should be given, and this will also include me going over the answers to them as well. All right. So you don't need to write this down, but stands for uh, initial change and then equilibrium. All right, that's what the ice stands for. All right, so here's how we pull into practice. So this first problem we have hydrogen gas is mixed with nitrogen gas. We're given their pressures, and then we're set at equilibrium. The pressure as pressure of atmosphere. Excuse me, ammonia's pressure of 2 atmospheres. We're looking for Kp. So, you know, in order to find Kp, we would need to know at equilibrium. All right, the pressure of NH3 squared, the pressure of H2 cubed, and the pressure of N2 to the first. The only thing we know currently is this, because at equilibrium, we know that. But without knowing H2 or N2, we can't solve for it. And we can't use these values because this is what it started with. It doesn't say this is what is at equilibrium. So we can't use the 6 for the 1.5. We know they have to go down because the system started with just reactants and then we had products produced. So we use an ice chart to help us solve this. So here's how you kind of go about doing this. And this works really for no matter any type of equation. It's the same setup. So I start by writing the equation up top. So 3H2, N2, arrow, NH3, ICE. Okay, so we know that at the very beginning that this value is 6. We know this value is 1.5. We know this is 0. And we know at equilibrium, this is 2. All right, so now let's look at the change, right? By the way, 6 from here, the 1.5 came from here, and then the 2 is from there. Okay, so let's think about this. When this reaction occurs, all right, we know the H2 and the N2 have to go down. So we know they both have to change by some negative amount, and the NH3 has to change by some positive amount. Well, we use our coefficients to help us figure out the rate of change. So when one reaction goes by, when one of these reactions occurs, 1 mole of N2 decreases. So we don't know what the actual amount's going to be, but we know it's going to disappear by a factor of 1. So we're just going to call that X. Okay. The hydrogen disappears by that same factor X, but 3 times as fast. So minus 3X. All right. And then the ammonia is going to appear at that same factor times 2, 2X. Right. Now, if we look, we know everything for the NH3. And we can write this as an equation. 0 plus 2X equals 2. Turns out we solve for this, X is 1. And now we can plug this in to both of these things. So for hydrogen at equilibrium, it's 6 minus 3 times 1. And for N2, it's going to be 1.5 minus 1. So that means at equilibrium, this is going to be 3, and this is going to be 0.5. right? And now we know everything we need. So now we can go back, right? We wrote Kp equals NH3 squared over H2 cubed N2. Kp equals 2 squared over 3 to the third times 0.5, right? And then if we solve, got 0.296. Right? And by the way, you can make this other statement even though it doesn't ask for this. Since Kp is less than 1, let's say this is reactant Kp. So let's try another one. All right, a vacuum vessel had 8 atmospheres of nitrogen pumped into it along with 12 atmospheres of hydrogen. At equilibrium, the pressure of ammonia is 4 atmospheres. Calculate K. And then what is K in the reverse reaction? Very similar setup, right? So let's try this again. So 3 H2, N2, 2 H3, ice. Okay, so zoom in. So 8 is the nitrogen, 12 is the hydrogen. This is nothing, and this is 4, right? Again, we know that this is going to disappear. The nitrogen disappears, the ammonia appears. It appears at some value or some rate we're going to call X. Ammonia appears at twice that rate. Hydrogen disappears at 3 times that rate. We know everything over here. 0 plus 2x equals 4. X equals 2. We plug x back in. 12 minus 3 times 2. 8 minus 2. We get 6. We get 4. Okay. And now we're going to plug everything in. It's the same Kp as before because the reaction hasn't changed. So it's going to be Kp equals 4 squared over 6 cubed times 4. Kp is 0.0185. Okay. So that is an ice problem. So that is an ice question. So the other question is, by the way, is what's the value of the reverse reaction? So if Kp is 0.0185, right? Remember, that's products over reactants. Then the reverse, these guys just switch roles. So now it's reactants over products. Kp, the new one, is 1 over Kp. 1 divided by 0.0185. 54. All right. All right. So the next step is something called the 5% rule. All right. So um, we use the 5% rule to help us estimate really small numbers. So I'm going to show you why we use it. Um, so if you're copying this down, all right, I'm going to write a bunch of stuff right now in pink. You don't want to copy this stuff down, right? Do not copy the pink down. All right, so we approached this just like before. So I'm actually just gonna slide this over. Okay, so it says this is 1.23, this is 0.738, and then this is nothing. And then it says find the partial pressure of each gas at equilibrium. So it doesn't give us really anything. So this is minus x, this is minus x, this is 2x. And if we add this up at equilibrium, this would be 2x. And then we don't know what x is. So this would be 1.23 minus x, and this would be 0.738 minus x. Now, if we plug this in, we would get this. Kp equals hi squared over h2 times I2. Right? Well, if we plug all of that in, we would be left with this. Kp equals 2x squared over 1.23 minus x, and then 0.738 minus x. And this ends up being a horrible quadratic mess. And this is not something that we ever have to deal with in AP Chem, right? No quadratic formula, all right, ever. So there's something that we have to kind of notice here. Let's go back up. Right? So now we're going to switch colors. So now we'll put, we'll go back to blue, copy the blue. Blue is good. The K value is really small, right? That's, really less than one. And because it's so far less than one, all right, we make this assumption that the value of x is super small. Right? So here's what we can do. We set up our problem just like before. So this is the H2, right? This is the I2, this is the HI, this is 2x, this is 2x, this is minus x, this is minus x. Okay. X, right, is thought to be so much smaller than the initial values that we just ignore the minus x. This becomes just 1.23. We can just forget about that. This becomes 0.738. We can just forget about that. Now, we don't ignore this one because anything is way bigger than 0. And right now it has nothing there. So we ignore it from the initial values, but equilibrium, we consider that x. Now, because of that, when we solve for Kp, it's so much easier. Kp equals 2x. That's the top value. That's the hi squared. On the bottom, it's just 1.23, right, times 0.738. Oh, and I totally forgot to write this. We know Kp. Get rid of this. Kp is 3.3 times 10 to the negative 6. So we can bring everything over. We can multiply the denominator by the other side, 3.3 times 10 to the negative 6 times 1.23 times 0.738. That'd be like 2x squared, 2x quantity squared, I'm sorry, equals 0.2 5 zeros, 2996. Right. So if we distribute that squared in, it was originally this. Now it's that. So we divide both sides by 4. And then we take the square root. And it turns out x, throw way up here, is 0.00086. Okay. So the question says, find the partial pressure of each gas at equilibrium. Well, if we plugged in this value for here and for here, with sig figs, it would round back to 1.23 and 0.738. So those numbers don't change. However, in equilibrium for the HI, it's going to be 2 times x. So the very last thing we're going to do is plug that into there. So 2x equals HI, 2 times 0.00086. Right, and you get HI's pressure is 0.00. 0.00172. All right, so we're gonna try one more of these. All right, so we have to find the concentration of H plus at equilibrium in this solution. So again, it's the 5% rule. So we have 0.23 as our initial, nothing and nothing. This is minus x. This is x and x. 0.23 minus x, and this would be x and x at equilibrium. We'd say Ka, if we plugged in our values, would be H plus, HCO4 minus over H2CO4. And then we can plug stuff in. Again, we're going to ignore this X here. This X right there, we're gonna get rid of it. And again, we can do that because Ka is super small. So if we plug all of our numbers in, we get 5.3 times 10 to the negative 6 equals x times x over 0.23. 5.3 times 10 to the negative 6 equals x squared over 0.23. Right? Multiply both sides by 0.23. Right. X, which is also the concentration of H plus, 0.0011. All right. Unfortunately, guys, I have to cut this one short. I hope to see you guys on Thursday. Bye.